This is section 9 of the ACT Math Manual. Section 9 is probabilities. This all starts on page 65 of the manual. Probabilities are very common on the test. They will show up at least a couple times on every test. First thing that we should do is talk about what a probability is. Now, the very common man-on-the-street definition for a probability is how likely something is to occur, which we can see right here. That definition really is insufficient, though, for the purposes of this test. We do really need to know exactly what the probability fraction is. You may want to pause the video and think about what the numerator and denominator of a probability fraction would be. I will go ahead and walk you through that right now. The numerator in our probability fraction will be the number of desired / specified outcomes. The denominator of this fraction will be total possible outcomes. And you might want to put in parentheses underneath or above and underneath outcomes. You might want to write events. Sometimes we will refer to things that happen as events, sometimes as outcomes. That's what the probability fraction is. It is the number of desired or specified outcomes or events, so desired, specified in the numerator, and the total possible outcomes or events in the denominator. Now that we have a definition of a probability, let's go ahead and do example 1, which should for most students be very simple. You may want to pause the video and work through this on your own right now. So this question tells us that we've got 15 shirts in a drawer. 6 of those shirts are white. 1 shirt will be selected at random, and we want the probability that the shirt will not be white. So our desired or specified outcome here is not white, and our total is the total number of shirts, which in this case is 15. Well, the not white shirts are simply going to be these 15 minus 6, the other shirts aside from the white ones. So that's going to be 9 not white shirts out of 15 total shirts, and we can reduce that either in our heads. I'm going to go ahead and use the calculator. We're going to do 9 divided by 15. We are going to math, enter, enter, and we're going to get 3/5. So that is the reduced probability fraction. So there is a 3/5 probability fraction, 3/5 probability that this shirt will not be white. Do note that that 3/5 we could also express as a 60% chance that the shirt will not be white. But when a question does ask specifically for a probability, they are looking for this fraction and not a percent. If they, for some reason, asked what is the percent chance that the shirt will be white, okay, we can answer 60%. But on probability questions, they almost never ask for a percent chance. One important point about probabilities, remember that numerator value, the desired or specific outcomes, that always has to be less than or equal to, I'm going to go ahead and highlight this. Desired or specific outcomes must always be less than or equal to, but never greater than the total. What that means is that a probability fraction, a probability value, must always range from 0, where there is no chance that the desired or specified outcome will happen, up to 1, which is where the numerator, the desired or specified, equals the denominator, the total. So for instance, in the previous question, if all 15 shirts had been white, then there would be a 0 out of 15 chance that the shirt we pick would not be white. And if there were no white shirts in the drawer, then there would be a 15 out of 15 chance or probability that we would pick a not white shirt. So again, probability values range between 0 and 1. They can be expressed as fractions. They can be expressed as decimals. Again, unless the question specifically says what is the percent chance that something will happen, we should not be expressing probabilities as percentages. So 0.25, 1/4, those would be valid values for the value of a probability. Now, a couple of other important points about probabilities. I'm going to go ahead and highlight these. Sum of the probabilities of all possible outcomes of an event or experiment must equal 1. So that should be fairly easy to see using the previous question. We have a possibility of getting a white shirt. That would be 6 white shirts out of 15. And then we have the possibility of choosing a non-white shirt. And those are the only 2 possible outcomes. So 6 over 15 plus 9 over 15 is going to equal 15 over 15. Again, the sum of all possible outcomes, white, not white. When we add those probabilities, we have to get 1. That is pretty much what we just illustrated there, illustrates this next point as well. The sum of the probabilities that an outcome or event will happen and the probability that that same outcome will not happen has to be 1 as well. Notice what we just did here. We did white plus not white. I already wrote that down up at the top, but I'm going to write it again since we're illustrating this second point. White plus not white has to equal 1. So again, the sum of the probabilities of all possible outcomes of an event or experiment must equal 1. And by the way, you know, if we go back to this previous question, if we have 6 white shirts and then we have, let's say, 3 red shirts and then we have 2 blue shirts, so this is white, red, blue, that takes us up to 11. So maybe there are 4 orange shirts. I don't know who the heck would want to buy 4 orange shirts. Somebody who's really into Halloween, I guess. If we add up the probabilities that all of those will happen, again, we will get 15 out of 15, which equals 1. So if these are our 4 possible outcomes, white, red, blue, orange, when we add all of those up, we must get a value of 1. When we add up all of those probabilities, we must get a value of 1. Let's take a look at example 3, which further illustrate the 2 facts that we just discussed. Pause the video, do these on your own. Shouldn't be too difficult for most students. So in example 2, we have the probability that the Mighty Ducks will win the league championship is 0.63. What is the probability that they will not win? Well, remember what we just said. We said that the probability of something happening plus the probability of something not happening, of that thing not happening, has to equal 1. So that's basically the probability of a win plus the probability of a loss or a not win. I'll go ahead and write loss, has to equal 1. The question tells us that the probability that they will win is 0.63. Let's just go ahead and put a P in there. We can subtract 0.63 from both sides of the equation that I've just written, and we get that the probability of a loss is going to equal probability of a loss, and we can do this in the calculator, is going to be 0.37. And again, that also illustrates this first point, that the sum of the probabilities of all possible outcomes of an event must equal 1, because the only 2 possible outcomes of this event, winning the league championship, the Mighty Ducks winning, is that they either win it or they lose it. So that example illustrates both of the facts that we just talked about. In example 3, probability of selecting an odd integer from set A is 3/5. What is the probability of selecting an even integer from that same set? Well, again, there are only 2 types of integers. There's even plus odd, so our probability of even plus the probability of the odd, don't worry about the notation here. I know I'm switching it up from the previous example. Probability of even plus probability of odd must equal 1. We know that the probability of an odd is 3/5, so that's probability even plus 3/5 must equal 1. We subtract the 3/5 from the 1, and we get, actually we subtract the 3/5 from both sides, and what we get is 2/5. And again, that can be done in the calculator if we need to. That is also 0.4. Next, we have to know how to calculate the probability that 2 or more events will both happen. Let's go through example 4, and then we're going to add a little bit more detail to this because the ACT has begun to test recently another variation of this type of question. So let's go through example 4. If you want to try it on your own, pause the video and do so. I'm going to work through it right now. A bucket contains 25 marbles, each of which is a solid color. Great. There's 14 red and 11 white. All right. Chloe will select 1 marble at random, and then without replacement, that's an important phrase. We'll come back to that in a moment. We'll select another marble from the bucket at random. What is the probability Chloe will select 2 red marbles? So what we're looking for here is we're looking for selection 1 and then selection 2. Selection 2. We're looking for them to both be red. We want a red marble for the first selection, red marble for the second selection. And the way that we determine the probability that will happen is, so this is red, we want red and red. The way that we determine the probability of this happening is we multiply the probability of getting a red on the first selection by the probability of getting a red on the second selection. So what we are going to do is determine the probability of getting a red on the first selection, and that's pretty easy. That's 14 out of 25. There are 14 red marbles. That's our desired or specified outcome. There are 25 total marbles, so that's the denominator of our fraction. So that's the probability of getting a red on the first selection. This phrase right here tells us that whatever marble we pick on this first selection, we do not put back into the bucket. And what that means is if we pick a red marble on this first selection, there will now be only 13 red marbles left for the second selection, and furthermore, there will only be 24 total marbles in the bucket. Because we have pulled out a red marble, we have to decrease the number of red marbles by 1. We also have to decrease the total number by 1. When we multiply these together, we're going to get somewhat of a big ugly number. Let's go ahead and do that. I'm going to do this with the alpha F1 sequence. Most of you should have calculators that can do this. So 14 over 25, I'm going to multiply that by, again, alpha F1, 13 over 24. And it's going to give me the result in most reduced form. That's one of the benefits of using the alpha F1 sequence. So that's going to be 91 over 300. That will be the probability that I will select 1 red and then another red on my second draw. Now we do need to talk in a little bit more detail about some related concepts here. Let's go to page 64. I'm going to go up. You just need to look to your left at the blank page to your left. And on page 64, we're going to write down some notes. Let's start with writing down 2 sets. Let's do x, we'll do some even integers, 0, 2, 4, 6, how about that? And then y, we will, actually let's add an 8 to that, sorry. Let's add an 8 up there. And then y will do 1, 2, 4, 5, 8, and 9. Just a couple of random numbers. And let's say we want to know what x, and then this weird symbol, kind of looks like a large N, x, and then that weird symbol y equals. That weird symbol is known as the intersection symbol, intersection. It is equivalent to an AND statement mathematically. And what that means, x intersection y, is we want the set that includes the values where x and y overlap, the intersection of these two sets. And if we look at these two sets, we can see that they intersect here. They both contain the value 2. They intersect here. They both contain the value 4. And they intersect here. They both contain the value 8. So the intersection of these two sets is the set 2, 4, 8. Those are the three values that are in x and in y. Now, the other symbol we need to talk about here is this guy. This is the union symbol, equivalent to an OR statement. And if I want the union of x and y, x union y, then what I'm doing is I'm taking all of the elements from both sets. I'm no longer thinking about intersection of the two sets. I'm thinking about everything from both sets. So everything from both sets here, doesn't matter if it's in one or the other or both, everything from both sets here will be a 0, a 1, a 2, a 4, a 5, a 6, an 8, and a 9. So all of these numbers, whether they are in x or y or both, it doesn't matter. When we're talking about union, we want everything from both sets, not just the intersecting points. So those two symbols, you may need to know what those mean. So now that we know that notation, we need to talk about how this notation will relate to or play into a probability question. And there is a chance that we will see something like this. And what that notation means, what it sort of translates to, is this is the probability of A and, remember we said that that intersection symbol means and, this is the probability of A and B occurring together. So this is what we encountered on the previous question. We wanted the probability of getting a red and then another red, and that is why we used 14 and 25 and 13 and 24. That was the probability of getting the first red. That was the probability of getting the second red. And what we did is we multiplied. So in these questions, that's the key. You multiply the probability of A by or and the probability of B. You just multiply the two probabilities. So if they say or had said, let's say there were 14 red marbles and 6 blue marbles, then what we would do is we would multiply the probability of getting, and then they asked us what's the probability of getting a red. So here, let me do a little new one here. So probability of getting red would be 14 out of 25. The probability of getting a blue would be 6 out of, let's pretend we're doing it with replacement this time. So after we draw this first marble, we're going to replace that marble into the bucket so that our total stays the same. So if they wanted to know what the probability of drawing a red and then a blue would be, we would just do probability of red, probability of blue, and we would multiply them together, and whatever we get would be the probability of getting a red and then a blue. Now, the slightly trickier one here would be this guy. What this means is the probability of A or B. Now, let's take a look. I'm going to do a little Venn diagram here. Let's say this is students on the soccer team, and let's say this is students on the basketball team. And let's say total students on the soccer team is 30. I have no clue how many people are on a soccer team, as you can see. And then let's say total number of people on the basketball team is 20. But there are, let's say, 5 students who play both. Well, what that means is there needs to be a 25 out here. There's 25 who play only soccer and 5 who play soccer and basketball, making a total of 30 who play soccer. And then over here for basketball, we have 15 out here playing only basketball, and then 5 in here playing basketball and soccer. That makes that 20. Now, let's also say that there are I don't know, 150 total students at this school. So this is what our Venn diagram looks like. We've got 150 total students. There are 30 who play soccer. There are 20 who play basketball, with this 5 overlap in between the soccer and the basketball. So what this means is that there are a total number of students of 30 plus 15. 25 plus 5 is 30 plus 15. So there's 45 total students who play soccer or basketball, right? Because the 5 students that are in the middle here in the overlapping section, we don't want to count them twice. In other words, if we just added this 30 and this 20, we would get 50. But there aren't really 50 total students playing soccer or basketball. There are only 45 students playing soccer or basketball, because the 5 students, 1, 2, 3, 4, 5, those little dots are students, teeny tiny students. Those 5 students, we don't count them once in soccer and then once in basketball. We count them only once in either soccer or basketball. If we count them twice, then we are overrepresenting the number of students. So let's say that somebody asked us for the probability of somebody playing soccer or basketball. Probability of sub. Well, we pretty much just figured it out, because we have 45 playing soccer or basketball out of 150 total students, and whatever that reduces to, if we want to reduce it, that would be our probability. If we want to look at this, though, in a way similar to how we did the AND question, here's what we would do. We would add the probability of selecting a soccer player, so that is 30 out of 150. We would add that to the probability of selecting a basketball player, which is 20 out of 150. But remember, when we add those two together, we get that 50 out of 150 that we just said we didn't want to get. What do we have to do? We have to subtract out the number of players that are both soccer and basketball, and that will give us the 45 out of 105. So what we are going to do is we're going to write this formula here. So when we want to find the probability of A or B, where A and B can happen together, okay, notice that's the key on these questions. This is known as non-mutually exclusive events. Mutually exclusive would mean, so mutually exclusive would mean that the events or the outcomes cannot happen together. But in this case, soccer and basketball can occur together. We can get a student who is in both of those groups. So for non-mutually exclusive events like we have here, where the two events can occur together, what we do for the probability of A or B is the probability of A plus the probability of B, but then we have to subtract out the probability of A and, my fault, that should be an intersection, A and B happening together. And again, that's what we have up here. We have, I'll actually model this down here. We have the probability of soccer plus the probability of basketball, and then we are subtracting out the probability of a student being on both the basketball and the soccer team, and we get that 45 out of 150. Now, I will tell you, if you get a question that allows you to set up a Venn diagram, you can do these questions this way also, and just get the 45 and do 45 out of 150 and be done with it. However, it most likely will benefit you to know this formula and how to use it. Now, for mutually exclusive events, okay, for mutually exclusive events. So let's say we've got that same scenario where we've got the soccer, the basketball teams. But let's say there's a third team. So this is soccer, this is basketball. There's a third team. What's really popular these days? Let's say badminton. I'm not saying that to bust on badminton. I just think it's a funny word. So let's say there's a badminton team. Hopefully I spelled that correctly. And let's say there's, I don't know, let's say that's really popular and there's 50 kids that do that. And now let's say that, so notice there's no overlap between the badminton and either of these soccer or basketball circles. And now let's say that the question asks, what is the probability of selecting a student who is on the soccer team or on the badminton team? I'm gonna write bad just so we don't confuse it with basketball. Well, in this case, since there's no overlap between the soccer circle and the badminton circle, there is no way that we could pick a student who satisfies both soccer and badminton. In other words, these are mutually exclusive events. If I pick a soccer player, I cannot pick a badminton player, and if I pick a badminton player, I cannot pick a soccer player because, again, they don't overlap. In this case, you would simply add the probability of each event. So soccer is 30 students. Remember, that's from up here, and it's the total in the soccer circle. So that's 30 out of 150. We would add that to the 50 who play badminton out of 150, and that gives us 80 out of 150. That would be our probability of selecting a soccer or badminton player. I'm going to give you one final example on this, because one of the ways they test this may involve a deck of cards. So if we're talking about selecting, let's say the probability of selecting a king or let's do a queen. Well, the first thing you would have to ask yourself is there any way to select a card that is both a queen and a king? And the answer is no. Selecting a king and a queen cannot happen together. So those are, again, mutually exclusive. If I pick a king, I exclude the possibility of picking a queen. And if I pick a queen, I exclude the possibility of picking a king. Those are mutually exclusive. One excludes the other and vice versa. So because these are mutually exclusive, remember what we do is we simply add I should have written this formula down up here. So the probability, so this is for mutually exclusive events. The probability of A or B would simply be adding the probability of A to the probability of B. So because these are mutually exclusive, we would simply add the probability of picking a king to the probability of picking a queen, which, if you know anything about cards, is 4 out of 52 plus 4 out of 52. There are 4 kings, there are 52 total cards. 4 queens, 52 total cards. That is 8 out of 52. If you want to reduce it, you can. Now, if they had asked what is the probability of picking a king or a heart, that's my best heart, a king or a heart, then these guys, these are not mutually exclusive. These are non-mutually exclusive. The reason they are not mutually exclusive is because in a deck of cards, there is a king of hearts. There is one king that has the suit of heart, and therefore a king and a heart can occur together. These are not mutually exclusive. We can get a heart and a king at the same time. So what we would have to do is our formula, probability of selecting a king plus probability of selecting a queen, and then remember we have to subtract out the sorry, not a queen, my fault, I'm going too fast, probability of selecting a heart, and then we have to subtract out the probability of selecting a king and a heart. And what those probabilities would look like is the 4 out of 52s from above. Sorry, not from above. My bad. So this is the probability of selecting a king. There's 4 kings. This is the probability of selecting a heart. There are 13 hearts in each deck. So there's 4 suits. 52 divided by 4 is 13. So there are 13 hearts. And by the way, if they did ask you a question like this, they would certainly give you all of this information. They would not expect that you are a card expert and know everything there is to know about a deck of cards. So don't worry about that. So there are 13 hearts in the deck. 13 out of 52 would be the probability of selecting a heart. But remember, we have to take out that 1 out of 52 probability that we will select the king of hearts. That is the overlap between king and heart. There is one card that satisfies that king heart overlap, and therefore what we would have here is we would have 4 and 13 is 17 minus the 1 is 16 out of 52. So there is a 16 out of 52 probability that we will select a king or a heart from a deck of cards. Hopefully all of that makes sense. I will tell you that the questions that test mutually exclusive and non-mutually exclusive events will be very few and far between. So if you're going for an extremely high score, you're going to need to know that stuff. If you're not, and if you're not going for that high of a score, let's say 33 or above on math, I wouldn't worry too much about this information, at least not at this point, not until you start getting to that level on math. Now, we have to talk about one more bit of terminology here, and that is the difference between dependent and independent events. Dependent events are events in which one of the events changes the probability of the other, and these up here would be really good examples of dependent events. The outcome of the first event, drawing the red marble, affected the probability of drawing a red on the second event. If we had replaced the first red marble after we picked it and before drawing the second marble, then these would become independent events. The probability of the first event has no effect, or I should say the outcome of the first event has no effect on the second event. A really good example of independent events would be flipping coins. When we flip coins, the outcome of one flip has absolutely no bearing whatsoever on the outcome of a subsequent flip, and that is written down here. We have a 0.5 probability that we'll get a heads on each flip, and that has no bearing on what we will get on any subsequent flip, which means coin flipping is an example of independent events. Now we do need to talk about one more thing when it comes to probabilities, and that is expected value. These questions have definitely been showing up with a little bit more frequency. I wouldn't actually worry too much about really deeply understanding expected value. I think you will probably get away with simply knowing the formula that we're about to talk about on these questions. So calculating an expected value, what you do is you determine find the sum of the products of the probability of each value and the value itself. We want to find the sum of the products of the probability of each value and the value itself. So let's just break that down first here. Product of a probability of a value and the value itself. So if we have the probability of value 1 and value 1, what we do is we multiply them, and then we do that for all of the values. We get the probability of value 2, we multiply that by value 2, and then we add that to the probability of value 3 and value 3 itself, and we add up all of those products of the probability of a value and a value, and that will be our expected values. So that we can see how this works on an actual question, let's take a look at example 1. I would read it all the way through. If you do want to try it on your own, you can pause the video and try it. I'm going to go ahead and work through it right now. Since for most of you this is the first time you're hearing about expected value, you might want to just work through it with me. So this says, in a game at the county fair, a spinner dial is randomly spun. The circular face of the game spinner is shown below. When the dial stops spinning, the arrow is equally likely to be pointing to any one of the 8 sectors, and the player wins the amount indicated in the sector to which the arrow is pointing. What is the expected value of a prize in this game? So here's what we do. We've got 8 sectors here, but really only 3 values. We have the $5, we have the $0, and we have the $10. I'm sorry, the $50. There is a 1, 2, 3 out of 8 probability to get a $0 amount. There is a 1, 2, 3, 4 out of 8 probability to get the $5 amount, and then there is a 1 out of 8 probability to get the $50 amount. So by the formula that we just talked about, what we would do here is we would do the probability of getting a 0 times the 0. Again, that's the probability of a value times the value itself. We add that to probability of getting a 5 times the 5 itself. We add that to probability of getting a 50 times the 50 itself. We do this in the calculator so we don't make any careless mistakes, although this first one should be really easy. That's just 0. We add that to 4/8 of 5. Again, you can do this in the calculator. I'm just going to go ahead and write 2.5. And then 1/8 of 50. I'm going to go ahead and do alpha F1, 1/8 times 50. And I am going to get 25 over 4. I am actually going to convert that to a decimal. I'm going to hit math, number 2, enter, enter. So that's 6.25. When I add up all of these values, what I get is 6.25 plus 2.5, which equals 8.75. That is the expected value of a prize in this game. Now, just to give you a little bit more detail on what's going on here, you might actually want to look at what the average is of all of the dollar amounts in these sectors. We have 0 plus 0 plus 0. That's the 1, 2, 3 zeros. We have 5 occurs 4 times, so that's 4 5s plus the 50. When we add up all of those and we divide by 8 and get our average, we will actually get exactly the same thing as our expected value. This is going to come out to 70 divided by 8, and if we go in the calculator and we do 70 divided by 8, 70 divided by 8 is going to equal 8.75, exactly the same thing. That's pretty much what an expected value is. It is really the average of all of the possible outcomes of a certain event. 8.75. The other way to think about this is that this number is what we would win on each spin if we were to play this game over and over and over again. In other words, in the long term, we would expect to win an average of $8.75 every time we played this game. That's what our average, that's what we would average out to. So if this game charged $5 to play, this would be a great game to play. You would end up winning quite a bit of money if you played this over and over and over again. If this game charged $10 per spin, probably wouldn't want to play it too much because you're going to lose $1.25 on average every time you play. So that is an easier example of expected value. Let's go ahead and do example 2. This one is definitely tougher. You might want to try it on your own, so pause the video and attempt it on your own. I'm going to go ahead and work through this one right now. So the question tells us that there's an office building with 40 offices that are available. The owners make an occupancy rate table. Keep in mind the occupancy rate is the fraction of offices that are occupied. So this occupancy rate of 0.6, which is like 6/10 or 3/5, that means 3/5 of the offices are occupied. And then we have the probability of the occupancy rate. Okay, that's that phrase there. And then based on the probability distribution in the table to the nearest whole number, what we want is we want the expected number of offices occupied in any given month during the upcoming year. So listen, there's 2 ways that we can approach this. And if you did try this on your own, there is a possibility you got an incorrect answer because of the way that you approached it. But it may just be the case that there was one more step you had to take in order to get the correct answer. So here's what I'm going to do. I've got values here, and I've got probabilities here. And remember, if we want to find expected value, we can multiply the probability times the value, do that for all of these rows in this table, and then add all of those products up, and we'll get our expected value. So if I do that times that, that times that, that times that, and so on, here's what I get. So I'm going to do 0.6 times 0.05, and I get 0.03. Then I'm going to do 0.7 times 0.05. I get 0.035. Then I do 0.8 times 0.5. That one is 0.4. Then 0.9 times 0.4. I'm going to get 0.36. So if I add all of these up, 0.03, I'm going to actually just do here, let's do 0.03 plus 0.035 plus 0.4 plus 0.36. So I add all of those up and I get 0.825. Now, if that's what you answered, you are incorrect. And the reason that you are incorrect is because what we have just determined there is not the expected number of offices that will be occupied. What this value, this 0.825, that is the expected value of the occupancy rate. Right? We were determining the expected value of the occupancy rate with these calculations because we were multiplying the occupancy rate values times the probability of those values. Well, the result of that expected value calculation will be the expected value of the occupancy rate. So there was one more thing that we had to do. We had to take that occupancy rate, 0.825, which you can think of as 82.5%, or you could even go in the calculator and do 0.825 math, enter. So what that means is this is an occupancy rate of 33 out of 40. Well, if we that's the fraction of offices. Remember what the question said. That's the fraction of offices that are occupied. Well, if we multiply that by the total number of offices, which was 40, what we get is 33. That is the expected value for the number of offices that will be occupied. The other way that we could have approached this is we could have immediately converted occupancy rate to occupied offices. And the way that we do that is we simply say, well, if there's an occupancy rate of 0.6, if we multiply that by 40, we will get 24. So an occupancy rate of 0.6 converts to a number of offices that are occupied of 24. The 0.7 would be 28 occupied offices. The 0.8 would be 0.8 times 40 would be 32, and the 0.9 times 40 offices would be 36. So now we have values for occupied offices. We can ignore the occupancy rate column now and simply multiply these occupied office values times their corresponding probabilities. So if we do 24, let's get that calculator back in here. Let me move this over a little bit. If we do, oops, that's not what I wanted to do. If we do 24 times 0.05, so that's 24 occupied offices, there's a probability of 0.05 times 0.05. That is going to equal 1.2. I'm going to write these down way over here, 1.2. Then we do 28 times 0.05. That one is going to equal, I made a mistake there, 28 times 0.05. That is going to equal 1.4. Then we do the 32 times the 0.5. That's going to equal 16. You can do that in your calculator if you need to. And then 36 times 0.4. I'm going to do that one in my calculator. 36 times 0.4. That's going to equal 14.4. And if we add up all of these numbers in our calculator, 1.2 plus 1.4 plus 16 plus 14.4, magically we get the same thing that we got before. We get 33. So again, it's really just a matter of paying attention to what the question is asking. And from there, you have one of two options. You can first find the expected value for the occupancy rate and then multiply that value by the total number of offices to get the expected value for the number of offices occupied. Or you can just convert occupancy rate to a number of offices occupied and then use these values for occupied offices in your estimated value your expected value calculations. So that is expected value. One final note at the bottom, you should know that you might see some sort of nasty or intimidating terminology on expected value questions. My advice to you is to not be all that intimidated by it. As long as you know the expected value formula, you should be able to work your way through most expected value questions. And some of those questions that have the most intimidating terminology are actually the easiest expected value questions, where you simply have to multiply some values by their probabilities and add up all of the results. So that's basically it for probabilities. Important to know the terminology, what a probability actually is, what the allowable values for a probability are. Got to know some facts about probabilities. Keep in mind you will need to understand how to calculate probabilities of something and something else happening, or probability of something or something else happening. And then, of course, expected value. You should know a little bit about expected value, what it is, and certainly should know the formula. Most expected value questions are not all that difficult if you do know the formula.